morning, everyone. Thank you for coming. My name is Carly Soos. I am currently finishing my fourth and final year towards my degree in astrophysics here at Cal Poly Pomona. My research this past year has been on the SPICY Milky Way and evaluating the reliability of the SPICY catalog. So to begin, I wanted to define a few astronomy terms. So first, we want to understand what even is a YSO. YSO is an abbreviation for young stellar object, or essentially a baby star. In the diagram below, we see the basic process of the birth of a star. It begins when part of a cloud condenses into a central star with a protoplanetary disk, eventually turning into a pre-main sequence star and ending with a central star surrounded by a planetary system. The disks surrounding the YSOs are very, very bright in the infrared, which is one of the reasons that we use infrared observations to find these young stars. Keep in mind, this is a simple diagram as it only depicts one star forming, free from the effects of any other nearby objects or stars. In reality, the majority of stars form in dense regions as fragments of clouds collapse. Next, I wanted to explain what is SPICY. SPICY stands for the Spitzer-Iraq Candidate Young Stellar Object Catalog, developed to inventory young stellar objects across the sky into one convenient list for astronomers. On the right, we have an image of the Spitzer Space Telescope, which is essentially our infrared version of our own Hubble Space Telescope. The SPICY catalog was formed using mid and near infrared observations of the sky, as well as a machine-trained algorithm using a custom set of rules drawn up by my own research advisor to find YSOs. These rules handpick likely YSOs out of any older stars that may have been observed. Even with the relatively small portion of the sky SPICY has scanned seen at the bottom, the catalog contains almost 120,000 entries, which were identified from more than 100 million sources initially measured, or about a 1 in 1,000 chance of finding a YSO. Finally, I wanted to explain a little bit about reddening and extinction. Interstellar reddening is the scattering or absorption of light that results in a star appearing to us more red than it actually is. Reddening is a result of light passing through dense clouds or dust on their way from the observing stars to the observing telescopes. Interstellar reddening is less effective when it comes to infrared light compared to visible light, which is also why we use infrared to find these YSOs, as we are able to see through the veils of dust while also being able to see those bright glowing disks around the baby stars. An effect similar to reddening is called extinction. This is a result of when the scattering or absorption of the photons cause a star to look more dim than it actually is. Both reddening and extinction can affect observations in SPICY by making older, farther objects appear more dim and red, like YSOs, as their light passes through the interstellar gas and dust clouds. An example is when a red giant is located far behind the cloud of dust from the observer's point of view. These red giants can appear to be baby stars in the SPICY catalog, which is why we need to analyze the catalog for any suspicious contaminants by looking at their colors. The focus of my research is to perform a deeper analysis of the SPICY catalog to sort out any contaminants that have been passed through the set of rules to identify the baby stars. These sources could be red giants masquerading as young stars due to their position behind the dust that causes us to look at them like candidate YSOs. By identifying and observing these discrepant sources further, we begin to understand why these contaminants are in the catalog and furthermore, why they should be taken out. This brings us to the regions that I compared within SPICY, the Lobster Nebula on the left and the Cat's Paw Nebula on the right. On the top, we have the Vista infrared images, and on the bottom, we have the Spitzer near infrared images, which are what SPICY uses to identify the YSOs. The reason for observing these regions specifically is because they are dense star-forming regions. These are regions previously observed by members of my own research team to contain at least 10,000 stars in each region. This is a color plot, or a plot that can display the color of an object depending on where it lies on the graph. On this plot, an object is more red as it moves up the y-axis and to the right, whereas it is more blue as it moves down and to the left. Interstellar reddening due to any foreground dust will cause the object's y position to move on this plot. The x-axis has the effect of reddening from the presence of a disk glowing in the infrared. This plot overlays points from the cat's paw region of SPICY data in color over the points from all of SPICY in gray to observe and compare the distribution of their points. On the plot, you may notice there is an observed two-wing shape that looks almost like a butterfly. The valley that cuts between the wings is due to it being a region populated mostly by normal older stars, which have been removed from SPICY as expected. The lower wing is outlined in blue and is where most of our data points are located. This lower portion represents YSOs, and as we approach the smaller upper wing outlined in red, our points begin to include older stars mixing in with the YSOs. This suspicious upper wing is the focus of this analysis in order to separate the true YSOs from the background contaminants. Now, if we take out the gray data points representing all of SPICY, we are left with the red and blue points that are only from the Cat's Paw Nebula version of the SPICY catalog. As mentioned before, if a star is reddened, it moves up and to the right with a 1-to-1 ratio on this graph, but we want to de-redden these points. And to do that, we will move them down the 1-to-1 line until they reach the cyan line being a rough estimate of the bottom edge of the lower wing. For example, we can take this blue point here and move it down the red line, which has a slope of 1, until it appears here on the cyan line. The difference between the original y value of the point and the new y value of the point is what is known as the excess of this color space. The excess is the measurement of the amount of reddening that each star experiences. Here I have two histograms displaying the distribution of the excess values described in the previous slide. The blue data represents the lower wing objects, where the red data are the upper wing objects. The left shows the plot of the data from the Cat's Paw Nebula and the right from the Lobster Nebula. We can see on both plots that the upper wing data decreases and then spikes in the bin after a value of 1.5. This leads to suspicions concerning how reddened the objects are, leading us to believe that they are background red giant contaminants not located in our nebulae, nor are they the baby stars that we are searching for. There are 26 total sources above this 1.5 excess out of the 876 total measured in SPICY for these two regions. This leads us to our conclusions. If we assume the limit of the excess to be 1.5, only about 3% of the sources in each region are lost. This leads us to believe that SPICY is accurate in identifying a young stellar object, as there are few contaminants. However, there is still more work to be done. The next steps of this project will be to test a similar analysis on the other regions measured by SPICY and to compare the results so we may work our way towards a more comprehensive list of YSOs. Thank you.